welcome today Hirokazu Shirado, who is an assistant professor at the Human-Computer Interaction Institute in the School of Computer Science at Carnegie Mellon University, which is in Pittsburgh, Pennsylvania, I heard.
Yeah.
Therefore, we rescheduled the timing of the seminar today to start later to make it a bit more convenient for Hiro, although it's still early in the day for you, I believe.
It's okay. Yeah, thank you.
Thank you so much for accommodating us. Hiro obtained his doctorate in sociology at Yale University. I believe that was last year, right?
Yeah.
And where he was a member of the Human Nature Lab at the Yale Institute for Network Science. And prior he got to Yale, he spent 8 years as an engineering researcher at Sony Corporation. And according to his bio, his overarching research interest is in the role of social interactions and technology in the emergence of social order. Very current topic these days. And in the collective confrontation of social dilemmas. In particular, he focuses on social networks and the implications of social network characteristics for network interventions. At the same time, he has been developing new methodologies in computational social science. And his experiments have contributed primarily to the field of sociology and human-computer interactions, also relevant to subfields related to network science, evolutionary ecology, behavioral economics, organizational theory, and public health. So that's a lot of fields that are also present in our cluster, and therefore you are the perfect match for our Monday seminar, and we're really excited to hear your talk now. Thank you very much.
Thank you very much. Yeah, thank you for great introduction. I'm happy to share my work with you guys at Center for Advanced Study for of the collective behavior at Constance. My talk title is Disastrous Effect of Human Networks in Emergency Coordination Experiment. In this talk, I'm introducing one of my recent work about social coordination in emergency. So as a researcher in computational social science, I'm studying the inter-individual dynamics of social dilemmas and collective action problems in human networks. Humans, like some other animals you have been studying, have evolved the ability to form complex network of social connections. However, the interconnected groups of people face challenge in collective action. Individuals may see no optimal way to act when individual and group benefits are not aligned. So collective action problem is deeply related to a fundamental social question about the emergence of collective order. How is our society possible? Based on the rich theoretical background, I've been exploring a sustainable technological intervention to narrow the gap between individual and group interest. So as for methodology, I primarily use experiment with many thousands of online participants embedded within social networks in small groups. This slide shows my experimental system. I often recruit human subjects from Amazon Mechanical Turk, that is online platform for some small works with small payment. And I let them pay some economically incentivized social interaction game online. Then I analyze their behavior data at both individual and group level. So in other words, I create small artificial societies of actual people to study social dynamics. Experiments have a different strength from observation study. In return for losing some realism, experimental study offers us a robust causal inference by researchers controlling study environment. Moreover, the advantages of online settings are many, including the ability to recruit large samples quickly and the ease of conducting many replicates of experimental treatment. So recently, I have been focusing on two approaches for collective action problem in social networks. So the one is network intervention. As Alexandra kindly introduced me, I've been studying the implication of social network characteristics for network intervention, such as tie rewiring, wealth inequality and visibility, and adding the noisy bot into human networks with a traditional theme of cooperation, and coordination. At the same time, I have been developing new methodologies in experimental social science to examine social dynamics in a more specific social context, such as resource sharing or emergency response. Today, I'm introducing one of my recent work from the latter category. The work is about social coordination in emergencies. Just a couple of weeks ago, the study was published by Proceedings of the Royal Society A for the special topic of network science. So if you are interested in today's talk, please check the paper later. The paper's title is Collective Communication and Behavior in Response to Uncertain Danger in Network Experiments. This study was inspired from my own experience of Japan earthquake and tsunami in 2011. On occasion of emergency like this, social coordination is potentially more important than usual. With a natural disaster approaching, prompt and reliable information exchange would be essential for people's safety. But on the other hand, coordination is more difficult than usual. In reality, many network phenomena, such as spreading false rumor and network disintegration, often prevent efficient social coordination, like the fake news turmoil in the last presidential election in the US and in the current COVID-19 pandemic all over the world. When this earthquake occurred, I was in Tokyo. Fortunately, Tokyo wasn't directly damaged by the disaster itself, but I suffered a lot from the false rumor and panics, especially online through my social networks. So I really wanted to know what's happening, so I analyzed the Twitter data. This is an example of false rumor tweet after the earthquake in Tokyo. Please spread to those people who live close to the east shore of Tokyo Bay. Due to the explosion of oil tanks, harmful chemical materials will fall with rain soon. Bring your umbrella and raincoat with you to protect your skin from the dangerous rain. This warning quickly turned out to be false with no scientific basis, but many people spread the rumor via Twitter. So the right figure shows, which is not from my paper, shows a snapshot of the retweet network about the dangerous rain tweet. The false warning lasted a full day. Social media data like this offers great insight about such massive social phenomena, but it also has limitations. For example, when I analyzed the tweet data, I found it difficult to trace information flow directly from the recorded data. Also, such social media contained what people said, but didn't contain what they actually did. So I decided to use this experimental scheme to supplement observational study like Twitter data analysis. When I started the research project, I wasn't able to find an appropriate economic game to study social coordination and behavioral decision-making in an emergency. So I invented a new social game called Evacuation game. So I said the subject receive $2 plus alpha, then if a disaster strikes, they lose everything. Subject earn 0 bonuses. So in the game, I give subject a behavior option. Subject can evacuate a possible disaster by responding $1 from their endowment. So evacuated subjects are not involved in the disaster. Even when a disaster strikes, they still earn $1 and more. So the game's point is very simple, just finding out whether a disaster would strike and select a correct behavior. If a disaster is going to strike, they should evacuate before it happens. Otherwise, they should stay on site to the end. So like a telephone game, subjects are allowed to communicate with local neighbors in a network. Then a randomly selected subject gets truth, that is official true information about disaster, For example, in this case, this orange guy was randomly selected to be an informed subject. So this player gets the official true information about disaster in advance. If the session has a disaster, the message says a disaster is going to strike. If the session doesn't have a disaster, the player gets the information saying there's no disaster. So if subjects spread accurate information originating from this informant to all over the networks, they can collectively choose a correct action. They don't need to rely on their random guess with interpersonal communication in this game. So let's see this player's game view. This player are not selected to get an official true information in advance, but one of her neighbors, this one, is the informed subject. Players can see only the local situation. For this session, this player is in a 40-player network, but she can see only 4 players of them directly. So here, 1, 2, 3, 4. Each player has 2 signal buttons, safe and danger button, and 1 exit button here. They can see the signals of their own and their neighbors in this network diagram. Also, they can evacuate by spending $1 to click this exit button. Once they click this exit button, they cannot cancel the decision and cannot come back to the game. So that means that they cannot send the signals anymore to their neighbors. So as I said before, this player wasn't selected as an informant. So she has the uncertain message in the page header saying a disaster may or may not strike. On the other hand, she is informed that one of her neighbors here is an informant indicated as I in the network node. So let's see the demo example to show how players communicate in the game. This is just a demo, not real game. But when people click the save button, their node color turns to blue and her neighbors can see the color change. The node color fades out in 5 seconds. And if she clicks the danger button, the node color turns to red and her neighbors can realize it. They can click the signal button anytime they want. So for this player, communicate with local neighbor to find out this situation is danger or safe to make a decision to evacuate. The game ends abruptly without advance notice. Nobody, including informed subjects, knows when it happens. So she was involved in the disaster because she didn't evacuate before the game ended. Her bonus was 0, unfortunately. So this player didn't click the exit button, but players can also evacuate anytime. Like online communication, they cannot see the neighbor's evacuation directly, though. So they can guess, maybe my neighbors evacuate because this player cannot send a signal for a long time, but they cannot see the behavior directly, like Twitter or the other SNS communication. This table summarizes the player's payoff structure. So in addition to the base bonus, subjects who are not involved in a disaster earned 10 cents for every other player who took the correct action. The additional payment encouraged players to share accurate information with others. So in sum, subjects were incentivized to stay individually because they have to pay $1 for evacuation, but also incentivized to be correct together with the worst scenario, stay, but it's incorrect. So I'd like to emphasize the payoff structure is asymmetric between staying and evacuation. So staying is high risk, high return option compared to evacuation. But there are no obvious incentives for players to send false information to lead to make a wrong choice. In addition, under even chance of disaster, so that means a 50-50 chance, the expected profit from evacuation is higher than that of staying. So as default, evacuation is a more economically rational choice than staying. Let's see how real humans behave in the game. This is a session of 40-node random regular network. So maybe some of you can realize it. Each player has 4 local neighbors in the network. So this player has 4 neighbors, this player has 4 neighbors, this player has 4 neighbors. In this sample session, a disaster is going to strike in 75 seconds. So in this video, the evacuated player are indicated with bold node like this, only for visualization. In the actual game, as I said, player wouldn't be informed of neighbor's evacuation directly. So please guess how many players would correctly evacuate from the disaster in 75 seconds. So I give you a hint because maybe their global situation depend on the informed subject behavior. So this informed subject would keep sending warnings correctly from 10 seconds to 30 seconds after the game starts. So how many subjects do you think have evacuated before a disaster strikes in 75 seconds? So the network has 40 players. And please think about it. How many players evacuate? For example, 0 or 10 players has successfully evacuated, or 10 to 20, 20 or 30, or 30 or 40. Please have your answer in my mind. Sorry about that. But yeah. So you can see the warnings spread through a certain part of the network, and people start evacuating with seeing the warnings. And the warnings are spread almost at the side of the network, but still you can see false safe messages spreading over the network. Then this informed subject evacuated. For example, you can see this subject keep sending warnings, but haven't decided to evacuate yet. Yeah. So a disaster strikes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Only 9 subjects have evacuated in 75 seconds in this session. So you might think, oh, this session should be outlier, but it's not. It's actually the average in the series of my experiment. Here, the aggregated result of dozens of sessions per treatment. In this study, I manipulated network size and topology. Each network had only one informant, so the network size increased, the fraction of informed individuals decreased. When a disaster would strike, the ring lattice network, this network, which are highly clustered, was significantly more effective for spreading evacuation behavior than random networks, especially when they consist of 20 nodes. This indicates network transitivity helps people to take the evacuation action in a network of small population. The diffusion dynamics should be different from a typical jump spreading, because if the evacuation behavior spread like germ, this random regular network should facilitate the diffusion process faster than ring lattice networks, because the path length from the informant is shorter in random regular networks. But the result is opposite. This ringless network facilitates evacuation diffusion faster than ringless network. That indicates people need to multiple signals in the decision making, known as complex contagion. I'll show the detail later. However, I want you to pay attention here on the result of another treatment that I haven't presented yet. That is the independent condition. In the independent condition, subjects didn't have neighbors, so they had to make a decision alone. Because they couldn't pass the information from an informant, most of the subjects had to follow their instinct. I know it's a dumb condition. However, you can see the gray lines of the independent conditions are above the colored lines of network sessions over time. That is, when a disaster would strike, the isolated subject made better decisions compared to the subject in a network and could access accurate information through interpersonal communication. On the other hand, when a disaster would not strike, more people in the network correctly stay to the end compared to those isolated. So the networks restrain unnecessary evacuations in the situation without disaster. This is good. But at the same time, networks also suppress necessary evacuation and encourage people to choose a risky alternative of the status quo. The comparison with the independent condition shows that social networks can make things worse, especially when people need them. The action taken by the group can also be thought as a collective prediction with a binary classifier. This graph shows the receiver operating characteristic curve or the ROC curve of the social prediction of a disaster. The ROC curve usually used for the evaluation of sensor systems. The annotated number indicated network size. As the network size decreases and the fraction of informant increase, that is this direction, the group level sensitivity of disaster prediction gets better. On the other hand, the false positive rate, that is the rate of false evacuation, keeps low in the network session. So the prediction accuracy improves with decreasing group size and increasing the fraction of informants in the network. That is reasonable, I think. However, the subjects within networks were slower in making decisions compared to those without networks. Networks fostered interpersonal communication that improve the overall prediction ability of a group, but at the same time put subjects at the risk for substantial loss in a time-critical situation by delaying their action. So we explored several different circumstances that might make network subjects evacuate more often than isolated ones. We focused on two additional features: post-evacuation information availability and structure heterogeneity. We tested the additional treatment thoroughly with the networks of 20 nodes. These additional treatments, however, did not make the social response to disaster significantly better than that seen in the independent condition. So for example, some sessions, we allow the subject to see the neighbor's evacuation, so they can see the actual behavior in addition to what they said. But still, in the disaster session, the network sessions were not significantly above the line of independent conditions. So the direct cause of procrastination is a spreading of false reassurance. This graph shows the average fraction of each cloud node over time in 40-node random regular network where a disaster does strike. So players send safe signals more than dangerous signals, even with a disaster. The spreading of safe signals overwhelms that of warnings over time, regardless of network size and topology, and even when an informant knew that a disaster would strike and correctly sent warnings. We also analyze the information flow with diffusion networks. This is a sample networks that use saw diffusion dynamics with the animation. Using the temporal and topological data of signals in this session, we reassembled this diffusion network of danger signals. So in the network, nodes represent unique players who are infected with warnings, and directed edges like this represented information flow. The horizontal axis shows the stream of time. We first identified the subject who sent a signal when their neighbors had never sent one as diffusion sources. So for this session, the informed subject, this one, was one of the diffusion sources, but the other, for example, these players also started the spread of danger signals without any prior information. When a subject sent a danger signals or evacuated after at least one neighbor had sent danger signals, we regarded the subject signaling as occurring in a chain of signal diffusion. So you can see some subject, for example, this player, sent a danger signal after they have received signal from multiple sources. We apply the same procedure to the safe signal diffusion in the same session. Just as a reminder, this session had a disaster and the safe signals were false. So the false message spread broader from multiple sources almost concurrently. Then we calculated the time elapsed after the chain sources sent the initial signal. For example, this diffusion chain, this orange line, has 4 infected unique players in sequence. We calculated the duration of each player from the diffusion source number 0. This graph shows the aggregated result of all the diffusion chain. We found that while safe signals spread significantly faster than danger, the diffusion speed has no meaningful difference with respect to the signal's veracity, so that is true or false. As a result, false reassurance, so that is this dashed blue line, faster than true warnings, so that is represented solid red line. Turning our focus to individual decision making, how does signaling from neighbors affect evacuation diffusion? This figure shows the actual behaviors of a subject and the signal exposure from her neighbors. This subject first sent 3 safe signals, but just before 40 seconds, she changed her view and sent 2 warnings. Then at 48 seconds, she evacuated. The signal from her neighbor should affect her decision making over time, but actual signal exposure is so complex like this, so that it's hard to clarify the causality with raw data. So I applied the Cox regression model to the data of individual decisions with time-varying covariance of the number of signals in neighbors. The behavior model shows the estimated cumulative probability of sending a safe signal, sending a danger signal, and evacuation under the fixed signal exposure from the start. For example, this cell shows the change of behavior probability, sending safe, sending danger signal, and evacuation when an average player continuously receives 2 safe signals and 2 danger signals from her neighbors. So we found with this analysis that danger signals actually more influential in receiver's behavior decision than safe signals. For example, when you can see this law, danger signals substantially increase the probability on sending danger signals, the red line, and evacuation, the green line, and reduce that of sending safe signals. So that means this blue line. So compared to the danger signals, safe signals, compared to danger signals, safe signals, for example, focusing on this column, safe signals do not have so much influence. For example, the blue line doesn't change so much with the increase of safe signal from neighbors. However, as default, like this situation, subjects are much more likely to send safe signals than danger signal. Furthermore, even without signal exposure, that is with zero safe signal and zero danger signals, subjects are less likely to evacuate compared to the independent condition. That is, the mere existence of social networks suppress evacuation even without signals when it's necessary. Lastly, I show another interesting finding from the individual level analysis. Before the game, each subject was asked with a 5-level rating system about his or her preference regarding risk, cooperation, and trust. So we found that risk-seeking subjects were less likely to evacuate without network interaction. But we also found individuals' risk preference had no effect on evacuation behavior with network interaction after controlling for signal exposure. So in the independent condition, risk-seeking subject are less likely to evacuate. That's reasonable because staying is high risk, high return option. But in the network session, this effect is gone. So the result shows subjects rely on the opinion of others instead of following their own inclination when they are embedded in networks. That is, collective communication can take over individuals' agency. In sum, our experiments show that social networks can work for the status quo. In the experiment, interpersonal communication reduced needless evacuations when there was no disaster, but at the same time, it also reduced necessary evacuation when there was a danger, even when a knowledgeable person in the group could correctly announce the existence of impending disaster. The reasonable asymmetric payoffs between the behavior options here can cause the propagation of the false negatives. These warnings, that is, the bad news, are valuable but undesirable message for people. Social influence can favor only one side, not to take a costly action, and can amplify disaster risk. So, of course, the result of laboratory experiment do not translate directly into the real world, but the experimental evidence suggests social networks may work poorly as information pathways for inconvenient truths, especially when it matters. So we couldn't find ways of improving the performance of social networks in this study, including the supplemental experiment. But I don't want to finish this talk with a bad end. So let me continue a little more to show some hopes. As you know, we cannot live without social networks, and I'm interested in how social networks can provide a benefit to individuals. So now I'm preparing a new series of experiments based on this evacuation game result, focusing on collective learning and network evolution. Okay, finally, this is my last slide. Thank you for your participation, interrupting my network. My study is mainly focused on improving the quality of collective action arising from interaction between people within social networks. Today, I talked about one of my studies about social coordination in emergencies. I would advance this frontier, and I hope it will give practical solutions to problems in collective action so as to reduce social network failure in the future. Thank you. And I also thank my research founders and colleagues for all their support. Thank you very much.
Thanks a lot for the talk. I wonder, so you were always comparing the independent person to the network, and I was wondering how much of the parameterization of the game drives the result, or the comparative statics between those two, because you can make many people abstain simply by changing the expected value of each of the options, right? and
Okay.
therefore yeah.
So your question is about the payoff structure. So maybe your concern, my result, depend on the one certain payoff structure. Is it right?
Yeah. So the comparison between what the independents do and what the groups do, that might depend on the parameterization of the game. That was my concern.
Okay. Yes. So of course, the result depend on the payoff structure. So actually, I tested several different payoff structure for this game. By changing the evacuation cost. So that means I fix the base pay, then I changing the evacuation cost from $0 to $1.5. Then I found we obtained almost the same result if we give the option with a small payment, even small payment of the evacuation give us the almost same result from this. So that means that even evacuation cost is just 50 cents compared to $2 base pay, they almost approximate the evacuation action. Then if we give free evacuation, so that means that there's no cost for the evacuation, yeah, they are almost, their evacuation rate increase and almost same rate of the independent conditions, but actually it's almost same as a random. So that means that if we give the if we give costless action option for them, so that means they have no payment for the evacuation, their behavior result is almost same as the independent condition. So that means that without disaster, they have a false evacuation a lot. So the point is, if we face some uncertain disaster and we have to pay some cost for necessary actions, I believe the subject in the network is proximate and less likely to take a necessary evacuation action compared to the independent condition. Did I answer your question?
Yes, thanks.
Yeah.
I have a question concerning this initial information. So as far as I understood, you said one person knew whether there is a disaster or not. So in that sense, the information is totally symmetric, which is in that sense astonishing that the response of the people is extremely asymmetric. So they essentially send no alarm or no danger messages. So those who are not informed usually send no danger messages, even though there is not really an asymmetric situation. Intuitively, this would make sense if the informed person is only informed about the disaster. Then it kind of would make sense that people usually say, yeah, no danger, no dangers. And as soon as there is danger, it spreads. And it looks a bit as if what you observe corresponds to such an idea. And it would be interesting to know what were people's thoughts about that. And then I have a remark which refers to the value of the social network. So in your social network, one problem was, of course, that people could not assess the quality of the messages. And so you had Twitter with, let's say, one letter. Now they increased it to 280 letters. And actually, perhaps one should introduce a minimum number of information that people provide in order to provide better information so that people can better assess whether this makes sense.
Okay, so let's try to answer the first question, your first question, and try to resolve the second one. So yes, the signal is symmetric, but the behavior related to signals is asymmetric. So of course, the message itself is symmetric. So there is no disaster or disaster is going to strike. But including informant, I think all subjects realize the consequence of the signals. So I think it's reasonable from the experiment settings and real world condition. And the second one is, I think the question is about maybe more complex communication affect the diffusion dynamics. Yeah, I think it's true. And that is important future work of my experiment. So that means if people can communicate well about their idea, their view, they might increase the efficiency of the evacuation decision making. But I think it may also reduce the efficiency by introducing another uncertainty in discourse. And also, my experiment covered certain features of social dynamics in emergency. So that in emergency, many people tend to exchange very short messages with each other, and they are key signals for the evacuation. So of course, maybe we modulated this experiment setting more conversational signals, but I think still this game shows some results of the evacuation. So for example, in the disaster context, several empirical works showed panic rarely occurs. Rather, people procrastinate in the face of the impending disaster with false reassurance. That is known as normalcy bias. So I think this study is kind of first one to reproduce the negative effect of human psychology with social networks and how social networks can amplify such a biases to take up people at the risk, in particular in the emergency situation.